Hello everyone, I'm Raghav and I'm going to be talking about how Go plays nice with your computer. So a little bit about myself. I'm a student at UCL in London, where I'm researching formal methods of verification. And recently, I've been trying to apply those techniques to the Go compiler and the Go runtime, which actually led me to write this talk in the first place. So let's start with the problem. We wanted more speed. Back in the old days, if you were unhappy with your processor's performance, all you had to do was wait for an upgrade. As long as your optimizations in that upgrade were valid, your valid programs run the same. Which, in other words, your optimizations are invisible to your valid programs. But because of Moore, we can't have that anymore. And we can't keep making the processor run faster and faster. So what's the solution? More processors. With more processors, you have more problems. Because this breaks the old assumption, which was valid optimizations are invisible to valid programs. Because now, even if those optimizations are valid for single threads, they can be visible to multi-threaded programs. So this example, in core 1, you have two simple assignments, x equals 1 and done equals 1. In core 2, you have a while loop, where as soon as done is not equal to 0, it breaks out of it. Now, the question is, can this ever print 0? You think no, because done is only not equal to 0 after x has already been set. But the real answer, it depends, which isn't good, especially if you're a cross-platform developer, right? If you're working with both ARM and x86, for example, it's not good because it depends on what hardware you're running it on. So in this case, if you're running it on x86 and ARM, for example, on x86, this will never print 0. But on ARM, it's possible that this prints 0. And that's because ARM allows for certain optimizations that are disallowed on x86. So certain reordering of instructions is possible in ARM. And that's because it runs on embedded systems. It allows for better performance, more energy saving, and things like that. What we want is a world without these surprises. Or more specifically, we want a contract. And a memory model is such a contract. A memory model is a contract between programmers, compilers, and hardware to determine what the deterministic result should be. Right? So in the case of the previous example, for x86, it's a strong memory model. It disallows certain optimizations, whereas for ARM, it's a weak memory model. The ideal model is sequentially consistent. Note, ideal does not mean good, but just the ideal case is if your memory model is sequentially consistent. What that means is that no matter how many processors you have, the result of running your program is as if you're running it on a single processor. So it's like you multiplexed all the instructions from all the threads onto one single processor, which means that all the instructions within each thread are preserved. So, in a sequentially consistent model, can you end up with a situation where R1 reads 1 and R2 reads 0? So in this case, over here, R1 is reading the value of y and R2 is reading the value of x. Because it preserves the order of instructions in each thread, that's actually not possible. No matter how you interleave these instructions, you will never have the case where R1 ever equals to 0 and R2 equals to, R1 equals to 1 and R2 equals 0. But what if this was on a non-sequentially consistent memory model? In this case, in the top right cell, the x and y assignments have been switched over because it's allowed in a non-sequentially consistent model, for example. And in that case, you can see that R1 and R2 have the value that is not possible in a sequentially consistent model. What this basically means is that you have a better way to reason about your programs if you know that it's going to be running on a sequentially consistent memory model. So what if your programs could run as if they were SC? And how does Go give us this world? Well, the Go memory model claims that, or guarantees that, if your program is free of data races, it will behave as if it is sequentially consistent. And this subset of sequential consistency is called data race-free sequential consistency, or DRFSC. So for example, in this case, these Go funcs are, these Go routines are implemented in a very racy way. Basically, the assignments to X and Y can be read before or after these Go routines run. So you can't really predict what's going to be the answer of your printlns. But this case, just by using Go primitives, I can make sure that my program is data race free. All I've done is move the assignment up. Right? So now, since this is DRF or data race free code, I know that Go guarantees sequential consistency. But what is synchronization really? How do we formalize something like synchronization? And we do that using the happens before relationship. And what that means is, in this case, say you have a concurrent system where you have thread 1, 2, and 3, and you have an event on A, some sort of channel send, for example, and it tries to sync with thread 2, which is a channel receive called A prime. And so it goes with B syncs with T3, with B prime, and C, and so on. Now, is it possible to reason about the order of these events? Can I make any ordering between A and C? Can I say that A happened before C? Well, yeah, because A prime definitely happens after A, because it's its sync event. B definitely happens after A prime, because it's on the same thread. Similarly for B prime, which happens after B, and C, which definitely happens after B prime, because it's on the same thread. So just by using transitivity, we have, can we say for certainty that A happened before C? Yeah. But what about this case? In this case, even though A prime and C prime are on thread 2 in that order, where A prime appears ahead, it's still possible that C happened after A, and just that sync event took longer. So we can't really make the call that A happened before C. And we'll see why making this call is important. Now, we make mistakes. We write code that can have data races, especially code like this, where we can't order. Imagine if A and C were two writes, and we don't know which one happened before the other. We don't know we can't expect the read to be either one of them, either one of the writes. So the hero we need is the Go race detector. What it basically does is it watches every memory access and checks for conflicting writes that aren't ordered by a happens before relationship. If they aren't ordered, they are concurrent, and there's potentially a race condition. If you just run the racy function that we showed earlier with the race flag, it'll tell you exactly which read and which write is racing, and exactly which Go routine which caused it, which is great. But before we dive into the race detector, how do we order events? How does the race detector know which events happen before the other? And for that, we need to dive into the physics of time and code. So the task is simple, right? We just need to know if event A happened before event B. But it's not simple. We can't use physical clocks. Without getting into too many details, it's just impossible to perfectly synchronize one master clock across all Go routines, for example. Just not possible in relativity, for example. What we come to is the fact that time is a partial order, which means that in the universe, every event cannot necessarily be ordered against every other. This takes some time to digest, but there are some sets of events or pairs of events that have no relationship between each other. Neither of them came before the other. They have no happens before edge. Basically, there is no total order in all the events that occur in the universe. So Einstein's big idea was speed of light is the absolute speed limit for information in the universe. Minkowski built on that and said that because of that speed limit, an event can only influence a subset of the entire region of space-time at any given time. Because there's a speed limit, it's only a subset of all events that an event can have an influence on. This is me when I was dieting for my gym goals. But this is what that subset looks like. We have, what this diagram is called is the Minkowski light cone model. And what this shows is the sphere of influence that I have on the universe. So my future light cone shows the events that I can have an influence on in the future. And my past light cone shows the events that could have had an influence on me. Anything outside the future and the past light cone are causally disconnected. It is not in the past, it's not in the future, it's elsewhere. Because if events in the elsewhere region had to affect me, information would have been traveling faster than the speed of light, which is impossible. So anything in the elsewhere region, if you want to affect it, you need to be traveling faster than the speed of light. That's the big idea. Now let's see how vector clocks actually capture this model of the universe. Anyway, Friedman-Mattern realized that this is the perfect model for distributed systems and concurrent programs. And he even wrote a paper about it, which I've linked to in my references at the end, where he talks about distributed time being a partial order and vector clocks. It's an amazing read. The speed of light in Go is the transmission of information. And this transmission can be a channel send, a mutex unlock, starting a Go routine, basically synchronization events. And these synchronization events are limited by the bandwidth of the network or the memory that you're running on. And because those bandwidths are limited by the speed of light. So now, pushing that analogy a little further, say you start with a Go routine now. The Go routines that it can affect are all in this future light cone. And similarly, the Go routine that affected it are in its past light cone. Any Go routine in the elsewhere region is concurrent, because there is no way that those events can be ordered by a happens before edge with this Go routine. So, yeah, because you would have to be traveling the faster than the speed of light. So vector clocks are essentially the light cone for your code. Let's start with Lamport clocks, so logical clocks. In this case, you just have one single counter per thread. And in this case, you have an event on T1. It increases this clock by 1. And then you have an event at T2, which the clock value for that is going to be 2 because it just sees the previous event and adds 1 to it. Similarly, there's an event, 2 events that happen on T3, 1 and 2, event on T2, and finally, it syncs with T3. And this is how the end state of your Lamport clocks will look like after all these events. Now, can you make any, can you say with certainty that these two circled events have a happens before edge between them? Like if either of these events happened before the other? Let's bring back our light cones. Now, just to note, these light cones are flipped, so the past is on top, future bottom, because time is flowing this way. You'll notice that the events that we were interested in are actually in the elsewhere region, so they're concurrent. But Lamport clocks fail to capture this, because according to Lamport clocks, the event on T3 happened before because it has a lower clock number, right? But that's not true. No way to tell that this event is in the elsewhere region. And we need to be able to say if it is, because that's what a concurrent event is. The problem is that it creates a total order, right? It forces order on events that have nothing to do with each other. The only thing that truly orders events is causality. Basically, could A have caused event B? Now, how do vector clocks solve this problem? So it's like giving each Go routine its own multidimensional clock. Each Go routine has a clock array, C1, C2, C3 for Go routine 1, 2, 3, for example, 1 per Go routine. And whenever there is a memory access on one Go routine, its own clock ticks up. So for example, if we start with a 0, 0, 0, it goes to 1, 0, 0, where the first digit is G1's own clock. Now, say G1 wants to sync with G2. G2 updates its own clock by taking the maximum of its own clock and G1's clock. So in this case, it sees that G1 had an event, so it updates its own first value to 1. It had an event on its own Go routine, so it increases its clock value to 1 and then 0. Similarly, there's 2 events that happen on G3. The clock values on the third position go up, and then there's another event on G2 which syncs with G3. This is the final state of our vector clocks. Did all of this extra information solve the problem that we had of trying to find out which Go routines were concurrent? Let's see. So still, those 2 events are still in the elsewhere region of the event that's circled on G2, right? So now let's say we add the final ingredient to our recipe of race detection, which is let's have both of these events be a write. So W2 and W3 are writes on G1 and G2 on the same shared memory location X, and you have more than one go routine. All you need to figure out is if these writes are concurrent, and if they are, that means that there's a potential race condition. We need a way to find out if these writes are concurrent. Right? So if a write from G3 is not ordered before or after from the write from G2, then they're concurrent. The clocks from W2 and W3 are not ordered because neither of them are strictly greater than the other. I mean, if you look at it again, W2 is 120, W3 is 002. Neither of them have all the spaces of the clocks larger than the other. W3 is greater in the third place, and W2 is greater in the first two spaces. So they aren't. They cannot have a happens before edge between them because neither of them is greater than the other. So race detected. Neither write could have caused the other. And the vector clocks capture exactly this. They both capture that these two events are in each other's elsewhere region in this Minkowski light cone model. Now, coming back to Earth, we have the thread sanitizer on LLVM that actually the Go race detector uses for its own race detection. And a few years ago, as part of Go 1.19, there was a gigantic update called V3. And there was a bunch of tweets about it. Unlimited number of Go routines, no more crossing fingers, faster race detector. I didn't even know that there was a limit on the number of Go routines that you can spin up. That was cool. And there's a CL for the merge as well. It says that it has a smaller shadow memory, fully vectorized calculation for vector clocks, smaller vector clocks, unlimited number of alive threads, Go routines, etc. And the really cool part is even with this gigantic change, the effect on Go was minimal. Apparently, all that was required was just rebuilding TSAN v2 and replacing it with TSAN v3, and it was all good to go, no breaking changes. So let's put that to the test. I was curious to look at those few claims, one about the unlimited Go routines and also the overhead between TSAN v2 and v3, if there were those improvements that they were talking about, and how much, if there were any. And for that, I wrote very simple tests. The first is this test Go routine limit function, where all I'm trying to do is spin up 10,000 Go routines, which seems like a lot. And I'm trying to keep them up, running in parallel, and for which I have a sleep for 1 or 2 seconds. And I have this benchmarking function. When I'm doing the same thing, I'm spinning up 10,000 Go routines, and I'm making a call to the Go scheduler manually because the default 10 millisecond preemption time was too little to have any decent number of Go routines up at a time. And I have a sleep for 10 milliseconds, which basically is some work that's happening within the Go routine. So, demo time, no pressure. So I have two environments, one with Go 1.18 and one with Go 1.19, right? So let's see what happens if we just try to run the test where I try to spin up 10,000 Go routines, right? So on Go 1.18, seems like it's going 6, 7,000, 8, and it does die at 8,000 simultaneously alive Go routines, exceeded dying, which is cool. What about Go 1.19? Okay, seems like it's at 9,000s, and we let that go on. But this same issue was actually exposed in the wild. As I was sleuthing through the issues page, I saw that somebody who was trying to run like a bunch of parallel tests on Go 1.17, I think, hit that same limit that we just did at 8,000 Go routines. And the next comment is one of my favorites on an issue. It's by Dmitry Vyukov, who worked on the TSAN runtime, who very casually says, I just happen to have redesigned the TSAN runtime that supports infinite number of Go routines, also twice faster and consumes less memory, which is just badass. But yeah, so it still seems to be going. I'm gonna accept his claim, and I'm gonna assume that yes, it does seem to work for more than 8,000 Go routines at least. But I also wanted to benchmark the overhead. So let's see what happens if I just run our benchmarking function. So over here, I'm just running my benchmark with the raise flag enabled, the same thing that I did for the test, and I'm running it for 10 iterations. And there we have it. So for Go 1.18, we get a value of about 200 million nanoseconds per operation. And let's compare that to Go 1.19. Same function, ran much quicker. And this doesn't seem like a lot yet, but it's actually almost an entire order faster on Go 1.19. More precisely, I think about 6 times faster, which is awesome. And when I ran this earlier, yeah, I mean, this was just contingency for if the demo didn't work. But when I ran it earlier, yeah, it was 6 times faster. But I wanted to know why that's happening. So I wrote another very simple function. And I just wanted to get the CPU profile, right, of TSAN. What's happening with V2 and V3 internally? Again, very simple function. This time, instead of 10,000 Go routines, I just have 5,000 because I wanted to stay under that 8,000 limit where Go 1.18 seems to die. And all I'm doing is that I have a simple counter that's guarded by a mutex lock. And I run this function for 3 seconds. Because I just thought that in 3 seconds, there'll be enough Go routines that are spun up, that there's enough contention for locks, and I have some cool profiles maybe. So let's run that. And for 3 seconds, and it collects some profiles. This was for Go 1.19. Let me get that for 1.18 as well. Yep. Now let's see what happens. Let's try to visualize our profiles, right? So already you can see some big offenders. The runtime is taking about 98% of the entire run. It's completely overwhelming the actual function that was running underneath it. And by far, the biggest offender is this sanitizer internal scheduler yield, which is taking 60% of the runtime. This is basically just a spin lock that's spinning, waiting for mutexes to unlock within the thread sanitizer. And because it's a spin lock, it's stopping all the processes from trying to make a syscall into the kernel. And of course, that adds a gigantic overhead. Also, when TSAN is trying to, when you run your code with the raise flag, TSAN is actually instrumenting the code quite a bit. It's adding a lot of flags, trying to keep track of all the memory accesses. It's reporting them to the runtime, which is adding up the vector clocks like we did in the slides. But let's see how that's different to Go 1.19. Already, the CPU profile looks very different, so clearly a lot changed in V3. But right off the bat, your runtime is, unlike the 98% that it was taking up, it's only about 53% of the CPU profile that the runtime consumes, and of which the worst offender is this compare exchange routine. So instead of, and this does sort of start giving hints to what may be going on. Instead of one spin lock, which stops all of the processes, now you have sort of a lock-free data structure, which can be run in a distributed way. So all of these syscalls for the lock can happen at the same time in parallel, perhaps. And it just takes 14% of the total runtime, which does give clues as to why there was such a huge drop in overhead, nearly 6 times that we saw. So, yeah, when I ran it last time as well, it was about the same. So some conclusions. We can't always write data race-free code, even if the Go memory model guarantees that if you do, you get a sequentially consistent execution of your program. For that, we need a powerful race detector because we make mistakes. The good news is the Go race detector is awesome. And TSAN v3 even more so. Even though the race detector does have some shortcomings, like it's apparently not as good as finding races if you use multi-word structures. It doesn't. You don't run it statically. You run it during runtime. And if that's a problem for you, that's a problem for you. But next, vector clocks model Einsteinian time, which, as of right now, is the most accurate model of the universe we have, which is why they work, which is why they're able to figure out which events are concurrent. And finally, right from the Go docs, I thought it fit to conclude, which was, when it comes to writing program with races, both programmers and compilers should remember the advice: don't be too clever. Thank you.